In today's video, we're starting chapter 4, which is where we finally get into integrals, which is kind of the second big pillar of calculus. There's derivatives and there's integrals. And to start talking about integrals, we're going to talk about a concept called antidifferentiation, which is where we're calculating antiderivatives. We're finding antiderivatives. So what is an antiderivative? Okay, natural first question. And to make sense of this, let's give ourselves a function. Let's give ourselves f of x is equal to x squared. Okay, nice, simple. We'll start nice and easy. So an antiderivative, you might be able to guess, is the opposite of a derivative. Well, what does that mean? What an antiderivative is now asking is, what function, when I take the derivative of it, will give me, for in our example, x squared? Okay, what function can I find? A lot of times with antiderivatives, we use a capital letter of whatever the function is. So in this case, capital F. What function out there can I find such that when I take the derivative of it, I get x squared? Well, let's think about it. We're working with a power function, right? X squared is a nice simple power function. In order for me to end up with x cubed, that means I should be working with some sort of x cubed function, right? Because when I take the derivative of it, I'm going to subtract 1 from the exponent, and that'll leave me with 2, right? Because 2 is equal to 3 minus 1. But I also have to recognize that my coefficient in front of this x squared is just a 1. But when I take the derivative of x cubed, I can't just leave it as x cubed, because when I take the derivative of it, I'm going to bring the 3 down as a constant in front. Well, what I can do is I can adjust for that by simply multiplying this by 1/3. Now, if I take the derivative of 1/3 x cubed, I'm going to bring the 3 down. 3 times 1/3 gives me that 1. All right, that's 3 times 1/3. And then 3 minus 1, subtract 1 from the exponent, I get x squared. So perfect. I was able to find a function that when I take the derivative of it, I get the function that I started with. I get x squared. So this is what's known as the antiderivative. Okay. Now, something to keep in mind with antiderivatives is there's actually an infinite number of antiderivatives. This is not the only antiderivative for this function. Can you think of maybe another one? Well, the key to this is recognizing that what happens when you take the derivative of a constant? It goes to 0. So technically, would this also be an antiderivative? Well, it's easy enough to check. Just take the derivative of it. When I take the derivative of 1/3 x cubed, I get x squared, right? I get x squared plus derivative of 5 is 0, and I'm left with x squared. So with antiderivatives, it turns out that there's an infinite number of antiderivatives because I can add just a different constant to it. And it still counts as an antiderivative. So if I were to give you a formal definition here of what an antiderivative is, the antiderivative of a function f of x, is the set of functions. And notice how I'm using capital F to represent the antiderivative. But I'm also going to put a plus c here. That plus c represents that I could put any constant there and it still counts as an antiderivative. Such that, what has to be true for it to be an antiderivative? It has to be true that if I take the derivative of my antiderivative, I get my original function. So I take the derivative of capital F of x plus c, I'm going to get f of x. Okay. We call this constant c the constant of integration. Okay. And that's always going to be there when you're working with antiderivatives, because you can put any constant there and it still counts as an antiderivative. So where are antiderivatives helpful? Well, now that we know a lot of different applications just from derivatives, since antiderivatives are just simply going the other direction, antiderivatives are just as helpful as derivatives in some cases. So, for example, if I know the velocity of an object, I can use the antiderivative to get me the position function, to know the position of the object. If I know the marginal cost function, remember the marginal cost was represented my derivative, my cost function. So if I know the marginal cost, I can take the antiderivative to get the total cost. And then any sort of rate of change, okay? And this one's important enough that I'll write it down. If f of x represents a rate of change function, okay? So if your function represents a rate of change like velocity or like marginal cost, any sort of function that talks about how something's changing, then your antiderivative represents the total change. So that's where antiderivatives can be really, really helpful. So let's see if we can come up with our basic antiderivative rules. That's what we'll do next. Okay, but before we get into our antiderivative rules, let's go over a little bit of notation, okay? So notation for antiderivatives is we use this really skinny s, okay? So if I do this really skinny s of f of x dx, and I promise, I'm going to explain this. I'm going to explain that dx, what that's doing there in a future video. But if I take the antiderivative of f of x, I get capital F of x plus c, right? I get my set of antiderivatives. So that really skinny s is how I notate these antiderivatives. That's going to help us when I start coming up with these rules. Okay, so let's come up with some rules for antiderivatives. First, what do you think is going to be true if I take the antiderivative of just a constant? So if I had some constant k, what's going to be my antiderivative? Well, think about it. What type of functions, when you take the derivative of them, just give you a constant? Linear functions, right? When I take the derivative of a linear function, I just get whatever the slope is, and that's a constant. So my antiderivative is just kx plus whatever, kx plus c. Remember, we're always going to have that plus c to show that there's an infinite number of different functions that work for this. Okay, so there's my constant rule for antiderivatives. Okay. Next, what about a power function? What's my rules for power functions? Well, we kind of hinted about this when we went through my opening example, x squared. In order to get a power function with this, with these antiderivatives, you're gonna do the opposite rule of your derivative rule. So instead of subtracting one from the exponent, you're going to add one to the exponent. So I'm going to have x to the n plus 1. Because once again, by taking the derivative of that, n plus 1 minus 1, you're going to get back to x to the n. And instead of multiplying by whatever your exponent was, I'm actually going to divide by whatever my new exponent is. And you can double check that when you take the derivative of that, you're going to end up with just 1 times x to the n. Okay, so that's my power rule. Let me keep track of this. This is my constant rule, and this is my power rule for antiderivatives. Next, what about something in this form? Oh, wait. Oh, I almost forgot. This rule works for all n values except for n equals 1. Sorry, n equals -1. It works for all n values except for n equals -1. Why is that? Well, let's look at that very specific case right now. What about 1 over x? You might be thinking how that relates to n equals -1. Remember, if you have a negative exponent, if I have x to the -1, that's the same thing as 1 over x. Okay, so this is this very special case where the power rule does not work. Why not? Because we should actually recognize 1 over x. What function, when I take the derivative of 1 over x, gives me, or what function, when I take the derivative of it, gives me 1 over x? And it turns out that's natural log of x. So that's why there's this one exception to the power rule. Okay. And if you forget that, if you try and use the power rule on this function, right, x to the -1, notice what happens when you try and use n as -1. You're going to get 1 over 0 for your fraction, which of course is a no-no. So if you try and use the power rule, you're going to run into that issue anyway. Okay, so there's my logarithm rule. And last but not least, what happens if we have e to the kx, right? If we have my natural exponential function, but now I want to take the antiderivative. Okay. Well, like I said, this is going to look kind of like the opposite of what the derivative rule is. The derivative rule is I'm just going to take that constant and multiply it by the front, leaving everything else the same. Well, since this is the opposite, I'm just going to divide by that constant. I'm going to do 1 over k times e to the kx plus c. So those are my antiderivative rules. And it's actually worth noting, okay, that there's actually a couple more that are worth noting. First of all, we had a nice rule. Well, we had a nice property with regular derivatives. Dang it, I want to write that in green. Where if I'm taking the derivative of a function that has a constant multiple in front of it, that's being multiplied by a constant, how does that affect your derivative? Well, we saw that it didn't really affect the derivative at all. You can just take the derivative of the function like normal and then multiply it by the constant. Well, because that's a rule for regular derivatives, that's also a rule for antiderivatives. Turns out you can just take the antiderivative of your function and then multiply it by that constant. Now, this is interesting. I could write it like this, but if you think about distributing this c, what's a constant times a constant? It's still a constant, which means I can just rewrite this as c times capital F of x plus capital C. I don't need to worry about distributing that constant because capital C already represented an arbitrary constant. Okay, and then what was the other operation that didn't affect derivatives, right? If you have two functions being added or subtracted together and you're taking the antiderivative, well, just like it doesn't affect derivatives, this also doesn't affect your antiderivatives, okay? And so what you're going to get is the antiderivative of f plus the antiderivative of g plus c. Now you might be thinking for this one, well, why don't I have a c for both of my antiderivatives? Well, because if you have two different arbitrary constants and you add them together, you end up with another arbitrary constant. So I only have to list the one constant. And this is my addition and subtraction rule. Perfect. So those are also important because these kind of functions will let me tackle like polynomials and things like that. Now, since I know those properties as well. Okay, I think we're ready to start on some examples. This example comes from your homework. And a lot of stuff going on with this one. So if I see that little skinny s in front, what is it asking me to do? It just wants me to find the antiderivative, the general antiderivative of this function. Okay. Now, I've got different terms being added and subtracted together. Well, according to my addition and subtraction rule, that means I can just focus on each of these terms individually and find their antiderivatives individually. Which means that if I wanted to, I could rewrite this like this, as three different antiderivatives. Sorry, I'm forgetting to put a dx after all of these. And now I can just focus on each of these individually. Okay, well, x squared is a nice, simple enough one, right? That's just using my power rule for antiderivatives, and I get 1/3 x cubed. Right? We've already looked at this example. And just to highlight what I was saying earlier, let me go ahead and put a c here, and I'm going to label it c1 because it's my constant for my first function. Well, this next one, remember, based off my constant multiple rule, that 6 isn't going to affect my antiderivative, which means I can pull it out in front of my antiderivative symbol. But then I don't have a rule per se for square roots, so in order for me to deal with this, I need to get this in terms of a power function. I need to rewrite this as x to the 1/2. Similarly, this third term, I need to do the same thing. I need to rewrite it as a power function. Well, this one, the x is in the denominator, which means my exponent's going to be a negative. A negative what? Well, I'm raising it to the third power and then square rooting it. So this is x to the negative 3/2. Okay, so I still have this 1/3 x cubed plus c1 minus the antiderivative of x to the 1/2 is going to give me 1/3/2 times x to the 3/2. I add 1 to the exponent and divide by that new exponent value. Oh, and then of course I'm going to have a plus c. I'm going to have a general constant for this second antiderivative. And then this one, I'm going to have 1/negative 1/2 times x to the negative 1/2 plus c3. And that's once again just using the power rule for my antiderivatives. Okay, let's clean this up a little bit. I'm going to have 1/3 x cubed minus, let's see, 6 divided by 3/2. I can just multiply by the reciprocal, so I can multiply by 2/3, and I get 12/3, which is 4, so I get 4 times x to the 3/2. And I'm going to leave all my constants for the end. Minus 1 divided by negative 1/2 ends up just being negative 2x to the negative 1/2. And then I've got all my, I'm going to put all my constants here at the end. So it's c1 minus 6c2 plus c3. So this is what I want to highlight here. And this is, I've kind of mentioned this earlier. What do I get when I do an arbitrary constant minus 6 times an arbitrary constant plus another arbitrary constant? Well, all this is just another constant. All you're going to get out, since I don't know what C1 is, or honest, it doesn't matter what C1 is, and it doesn't matter what C2 is, and it doesn't matter what C3 is, it doesn't matter what I put there. I can just sum all this up as just one constant. So when I'm taking these antiderivatives and I have multiple different antiderivatives I'm taking, you don't need to worry about that plus c until the very end. You don't need to worry about the plus c until the very end of your solving process. So sure enough, what I'm left with is 1/3 x cubed minus 4. I can rewrite this as a square root of x cubed minus, since that's a negative, I'm going to put that in the denominator, 2 over the square root of x plus c. Okay. So that constant is arbitrary, which means you don't need to worry about it until the very end. Next, let's look at an applied example. Okay, so this is another problem from your homework where it gives me the marginal demand function. If I see that word marginal, what does that mean about this? It means it's a derivative. So I get negative 4,000 over x squared. That means this function is a derivative, and what am I going to be trying to do? I'm going to be trying to find the function that gives me this derivative. I want to find the demand function. Well, since I'm working backwards, this is exactly why I'm going to use an antiderivative. That's what an antiderivative does, is it moves me backwards. It finds the function that will give me this derivative. Okay, well, in order to do that, that means I am taking the antiderivative of negative 4,000 over x squared. But remember, I want to relate this to a power function. So I'm going to rewrite this as negative 4,000 x to the negative 2 second power. All right, since my power function is in the denominator, I can rewrite it using a negative exponent. So that's what I'm going to take the antiderivative of. Okay, so I have a constant in front. That constant is not going to affect my antiderivative, so I can move it outside of the integral sign, of the antiderivative sign, my notation there. And then x to the negative 2, I can just use the power rule on. And I'm left with negative 4,000 times, let's see, I'm going to add 1 to the exponent and divide by that value. Well, that gives me 1 over negative 1 times x to the negative 1 plus c. Well, 1 over negative 1 is just negative 1, and so negative 1 times negative 4,000 gives me positive 4,000 times x to the negative 1. If I have a negative exponent, I can just move that to the denominator, and so that's what I end up with. I end up with 4,000 over x plus some arbitrary constant, and that's my demand function. That's my demand function. We'll write that as d of x without the d prime. But this is still, this demand function that I have, there's an infinite number of functions that would work for this because I can plug in any value for c and it still counts as an antiderivative. But in this case, for this specific company, they don't want an infinite number of demand functions. They want their specific demand function. So what do they give you to help you figure out what their specific function is? They give you a data point. So they tell you that the demand when the price is $4, so the demand when the price is $4 is 1,003 units. So they have a data point for us. They have an x value with a corresponding y value or corresponding output value. At $4, your demand is 1,003. How does that help me? Well, that helps me solve for C. I can plug in this data point and solve for what my C value is going to be. Okay? So where's the 1,003 going to go? That represents an output value. So that's going to go over here. What am I plugging in for X? My input value was $4. So that's what goes in for x. Okay. I can solve this a little bit. 1,003 equals 4,000 over 4 is just 1,000. So what does that mean C is? C is equal to 3. So there's a few problems on your homework where you can actually solve for the C value because they give you either just a data point or they give you an initial value. So make sure you're looking for that in the problem to see whether they give you a starting point or an initial value, or they're giving you a data point that you can plug in. So my final answer here, my demand equation, would be 4,000 over x plus 3. Okay, good luck with the homework. Let me know if you have any questions.